Today we are looking at proof by induction, a technique used to prove that a statement is true for every whole number starting from some fixed value. Proof by induction has two parts. The first part is called the base case. In the base case we show that the statement is true for the starting value, usually when n equals 1. The second part is called the inductive step. In the inductive step we assume the statement is true for some whole number n. Then we show that this assumption forces the statement to also be true for n plus 1. There is a different method called proof by contradiction. In proof by contradiction, we assume the opposite of what we want to prove. Then we show that this assumption leads to something impossible. Now let us work through a full-worked example of proof by induction. We want to prove that the sum of the first n whole numbers equals n times the quantity n plus 1 divided by 2. In symbols, this is written as sum from I equals 1 to n of I equals n times open bracket n plus 1 close bracket divided by 2. First, we check the base case, where n equals 1. On the left-hand side, the sum of the first one whole number is simply 1. On the right-hand side, we substitute n equals 1 into the formula. This gives 1 times open bracket 1 plus 1 close bracket divided by 2, which simplifies to 1 times 2 divided by 2, which equals 1. Both sides equal 1, so the base case is confirmed true. The base case is now checked and we can move on to the inductive step. Second, for the inductive step, we assume the statement is true for some whole number n. In words, this means the sum of the first n whole numbers equals n times the quantity n plus 1 divided by 2. In symbols, this is written as sum from I equals 1 to n of I equals n times open bracket n plus 1 close bracket divided by 2. Our goal now is to show that the same pattern holds for n plus 1. In words, this means the sum of the first n plus 1 whole numbers should equal n plus 1 times the quantity n plus 2 divided by 2. In symbols, this is written as sum from I equals 1 to n plus 1 of I equals n plus 1 times open bracket n plus 2 close bracket divided by 2. We start with the sum up to n plus 1. This equals the sum up to n plus the extra term n plus 1. Using our assumption, we replace the sum up to n with n times open bracket n plus 1 close bracket divided by 2, so the sum up to n plus 1 equals n times open bracket n plus 1 close bracket divided by 2 plus n plus 1. Next, we write n plus 1 as a fraction with denominator 2, so we can combine the two terms. This gives n times open bracket n plus 1 close bracket divided by 2 plus 2 times open bracket n plus 1 close bracket divided by 2. Both terms share a common factor of open bracket n plus 1 close bracket divided by 2. Factoring this out gives open bracket n plus 1 close bracket times open bracket n plus 2 close bracket divided by 2. This matches exactly the formula we wanted, with n plus 1 in place of n, so the statement is true for n plus 1 whenever it is true for n. Since the base case is true, and the inductive step shows truth passes from n to n plus 1, the statement is true for every whole number n by mathematical induction. To check our answer, let us test the formula directly for n equals 3. The sum of the first three whole numbers is 1 plus 2 plus 3, which equals 6. Using the formula 3 times open bracket 3 plus 1 close bracket divided by 2 equals 3 times 4 divided by 2, which equals 6. Both methods give 6, so the formula and our proof are confirmed correct.